we learned about that. And I was like,
Okay.
this guy can program.
Oh, we already looked at lecture 15. Huh?
Yeah.
So I was thinking about covering execution models today, but I thought it's important to discuss load store handling, something we haven't discussed as much. We discussed a lot on register handling, and I foreshadowed load store handling a little bit, so I'll cover load store handling. And then we'll talk about execution models with data flow. Although we have seen it, we'll now see how it actually works, how you can design a machine that is purely data flow at the ISA level. We'll see that out-of-order execution is data flow at the microarchitecture level. Okay? This should be fun. But before that, Lab 4 heads up. Lab 4A is already out. So you're going to extend your pipeline with branches. And you're going to do branch prediction. You're going to implement a global branch predictor and a tournament branch predictor. So that should be fun. That's 4A. There's also 4B, which will be out soon. And you'll handle branches in a different way. Actually, you'll handle pretty much everything in a different way by doing something else, right? Fine-grained multi-threading. You guys excited about this? Yes.
So I saw that the deadline for 4A is the normal 2 weeks.
That's right.
If 4B is out soon, will it also be due at the same time, or will it be due 2 weeks later?
No, actually, that deadline is incorrect. We fixed that deadline. The deadline for both is March 21st.
Is that in 4 weeks?
Which is, yeah, it's 4 weeks from now.
Okay, good.
So you have 4 weeks for Lab 4, which is good, which means that no one is going to use late days, right? Yes. I should hear a yes there. So you have no excuse to ask me for an extension. But the caveat is you should get started very early because the exam and spring break are within those 4 weeks, yes.
If you were to turn in both parts a day late, would you lose 2 late days?
Both? No. So this is, if you turn in both parts 1 day late, you'll lose 1 late.
Okay.
Wait.
Basically, the late day will be determined based on whatever you turn in the latest. Okay?
Is spring break before the 4 weeks?
That's right.
So this will be during this. Okay.
That's right. But you guys are hard workers, so you'll be
Be
taking.
done by then.
Yeah, exactly. You'll be either done by then, or you'll be taking your laptop to Cancun or somewhere. Right? That's a good place to work. Say it again.
I hope I go to Cancun for like spring break.
That's good.
I also don't think you'll get good SSH access with the DC machines.
Exactly. Yeah. I like that thinking. Yeah, you can do this anywhere in the world. But yeah, get started very early. Okay. And what I would suggest is finishing Lab 4A first and getting it checked off. Finish it next week. It's not that bad actually. The feedback last year was from many students was that they had too much time for Lab 4.
Why would anybody say that?
You can find who said that. And I would suggest finishing Lab 4B next time. Get that checked off.
Wasn't last semester with the MIPS process with them?
That was with the mid-trust, but it shouldn't change that much.
That was easy.
Yeah. You know, MIPS has a caveat, which is the branch delay slot, although we didn't have the students implement that last semester. So I guess it's not that much different. Okay. And do the extra credit too. So we have an extra credit for this lab, which is here, and we haven't decided whether or not we'll have an extra credit here. But you can optimize your branch predictor. You can design your own branch predictor and do better. So it's a branch prediction competition, basically. Now you won't see the effect as much because the pipeline is very narrow, right? It's not deep, basically. But hopefully you'll see some effect. And I would suggest, if you're interested in branch predictors, I would suggest implementing the perceptron predictor, for example, or other more complicated neural network-based predictors. So that could be interesting. Okay. Having said extra credit, I'd like to recognize those of you who've done extra credit for Lab 2. 5 people actually did it, which is better than last year. It was 1 person who did a microprogrammed implementation. Now we have 5 people, and these are the winners. And this is in terms of correctness. Albert, who was there. I guess you missed something over there. Next time, don't miss it. But this is good. This is a microprogrammed implementation, if you remember. Bailey, yes, you're here. Jeremy, he's not here. He's usually working at that computer over there. Clement, You're in the back? Okay. And Xian. Oh. And these are I think these are based on the correctness. Basically similar test that we ran for non-microprogram version. So I'd like to see 43 here, not 5. Hopefully next semester. Or for the next assignment. Okay? Okay. These are the readings. I'm not going to cover this again. Readings for next lecture, please do these because we're going to start vector processing in the next lecture. And this is a good paper that talks about GPUs. So if you're interested in that, this is a modern SIMD machine, single instruction, multiple data machine. And we're going to look at the basics of it. Okay. Okay, let's jump into the topic of today's lecture. We're going to talk about load store handling, but let me finish out order execution and remind you what we did. Actually, it's behind this, right? It's still there. Well, I don't want to go over that again, though. You can watch the lecture if you missed the example that we had. Basically, we looked at a machine that looks like this. You fetch instructions in order, and then you get instructions out of the way of other instructions, such that independent instructions can get scheduled in data flow order. This is the first comp where you place instructions to reservation stations, and then instructions get dispatched out of order, out of program order, but in data flow order. And they broadcast their values and tags such that they can wake up dependent instructions. And later they get reordered such that you can maintain precise exceptions. This is basically a modern out-of-order machine that we have today. And this is a summary that I ended up with. I'll briefly remind you what we talked about. Basically, we had 4 key concepts. First, we used register renaming to eliminate false dependencies and also to link producers to the consumers, right? That's how we woke up instructions, by that linkage. We buffered instructions to enable the pipeline to move forward in the presence of dependencies. Dependencies do not stall the pipeline anymore. We use tag broadcast. Remember, a functional unit broadcasts the tag of the instruction that's finishing to enable communication of values and the readiness of the produced value between instructions. Right? And you saw the complexity of this. We'll talk about that in briefly. Right? When you broadcast a tag, that tag needs to go everywhere in the machine that is waiting for that tag, which means that you need to have as many comparators as you have tags that are waiting for that broadcast tag. Make sense? As many as the number of reservation stations plus the register file or feature file entries. Right? Now immediately you can start thinking that if you make the reservation stations large, this becomes a limiter of cycle time or performance. Because you need to do that match in one cycle. Okay? And wake up and select once the sources of both, once all of the sources of an instruction have their tag broadcast or they're ready, then you wake up the instructions and the instruction, one instruction per functional unit needs to be selected. And this enables out-of-order dispatching of the functional units. So these 4 fundamental things enable out-of-order execution. Okay, we ended up here actually. Basically, I've told you that an out-of-order engine actually is a data flow machine, right? Basically, it really builds, dynamically builds the data flow graph of a piece of the program. It's not given the data flow graph because everything is in control flow order, but kind of dynamically builds the data flow graph. And you can actually infer the data flow graph by just looking at observing the machine itself. And we said that this could be a good reverse engineering problem, right? Could appear anywhere in the exam when you design your out-of-order processor, maybe 5 years from now when you're debugging, trying to see why it doesn't work. Which piece does it build? Well, it doesn't build the entire program, right? Because the entire program is huge. But it really builds the data flow graph, the portion of the data flow graph that's limited to the instruction window. The instructions that are currently decoded, but not yet retired. Or more appropriately, the instructions that are in the reservation stations currently. Right? Does that make sense? This is actually, the instructions in the reservation stations are the instructions that are not yet scheduled, right? This is the scheduling window. But you can, by looking at all of the state in the machine, you can construct the data flow graph in the instruction window. And that will be part of your... Actually, I think we have a problem in the homework that's similar to that. Can we do it for the whole program? Well, it's tough, right? Because then you need to buffer all of the instructions and have reservation stations as many as the number of instructions, the maximum number of instructions in the program. So this is very tough. Why would we like to? Well, if you have long latencies, maybe having more reservation stations is a good idea, right? And we'll do this exercise in a couple of slides. Basically, if you have the entire data flow graph, you can enable maximum parallelism in the machine. Right now, we're kind of extracting the data flow graph, and we're enabling parallelism from the part that's in the machine. We can execute independent operations that are within the instruction window. As you enlarge the instruction window, you can perhaps find more independent operations, right? Okay. Now think about this a little bit. This is well, we're going to get back to making out-of-order execution simpler later on. Basically, how can we have a large instruction window, right? I won't answer that question yet, but I'll ask you this question: can we do it efficiently with Tomasillo's algorithm? Remember, Tomasillo's algorithm has this tag match. It's very difficult to do this efficiently because as you increase the number of reservation stations, you need to broadcast that tag everywhere. For example, think about a machine with 1,000 reservation stations. Whenever a functional unit broadcasts its tag, all of those reservation stations need to compare the tags they store to the tag that's broadcast. So how many comparators do you need? 1,000 reservation stations. Let's assume one functional unit only, which doesn't make sense maybe, right? Because you are doing out-of-order execution. Let's assume 2 functional units, just as we assume. 2 functional units broadcasting 2 tags, 1,000 reservation stations, and each of them store 2 tags. Let's assume 2 sources. So you have 1,000 times 2 times 2. 4,000 comparators. That's a lot. And we don't normally have 2 functional units only. We normally have a functional unit per operation, right? Load, store. So as you add them, let's say 6 functional units, now you have 12,000 comparators. And the width of those comparators is the tag. Basically, width is proportional to the number of instructions that you can store in the machine, right? The instruction window. So they become wider as you increase the size of the machine as well. So the complexity of this increases quadratically. You can think about that too. With the size of the reservation stations, as well as with the issue width, if you will. The issue width is, or dispatch width, the number of functional units, in other words. So it's very difficult to do, even though Tomasillo, when he invented the algorithm, he called it an efficient algorithm for exploiting multiple arithmetic units. At that time, it was efficient. But today, it's difficult to expand it to a large instruction window. And we'll see mechanisms to approximate the performance of a large instruction window without building it later on in the semester, like run-ahead execution. Yes?
I don't know if I misunderstood this, but do you necessarily need more than one functional unit to do out-of-order execution? I guess by functional you mean like memory access is a functional unit.
That's right, exactly.
It's not just like a DSP and the ALU. It's like
That's right. Yeah, you need an adder and multiplier,
okay,
for example.
but
right?
it's fine if it's like the memory thing and then just an everything else unit. Right?
That's right. Yeah, that's also fine. Yeah, you could do out-of-order execution between memory as well as execute. And we'll see actually an architecture that's designed specifically for that.
Mm-hmm.
It's called decoupled access and execute. It's a limited form of out-of-order execution. And we'll see that later on. But yes, when I call functional unit, memory is a functional unit too. Okay, so keep these in mind. But let's look at the data flow graph for our example. You know how to build the data flow graph for this, right? If I give you this, you can build the data flow graph. Basically, you have a node for multiply, and inputs are R1 and R2, and R3 comes out. And you connect that R3 to a node for add, and then R4 is an input, R5 comes out, blah, blah. Okay, well, that's easy. Well, if I don't give you that, and if I give you just this, you should be able to build the exact same data flow graph. You guys have done this? No? Well, you'll do it. I'm not going to go through this example, but this is what I mentioned earlier, right? What I mentioned earlier is just by looking at this, you can build this. And you can infer all of this. Why? Well, you know which instructions are waiting, you know which instructions are executing, and you know which instructions, how the instructions are linked to each other, right? For example, here we know that you have a multiply whose sources are ready, and this is cycle 7. And we know basically we have 6 instructions, that are in the reservation stations. We know that 2 of them are multiplies, 4 of them are adds, and we know that the sources of this multiply are ready, and their values are 1 and 2, and they come from R1 and R2. So this is multiplying R1 and R2, and writing the result to tag X, and tag X is here. So it's writing the result to R3. So I'm going really fast, but you need to think about it a little bit more. Yes?
But you can't get the exact same piece of code, right? Because if you go back, the data flow graph assumes, or I don't know if it was forward, it assumes some sort of parallelism. So you could either do that add first, or the other add first, or the multiplication first.
That's right, yes. You may not be able to get the exact ordering.
Yeah.
And when we ask a question like that, we'll probably specify the ordering, or we'll give credit to both, basically. Yes, you may not be able to get the exact ordering of the instructions because you don't know which one will be is in the program order, right? But you should be able to get this.
Yeah.
Okay. So what is the data flow graph? A data flow graph, you've seen this before, but it basically nodes are operations performed by the instruction. Right? Here, for example, you have a multiply node, add node, and arcs are the tags in the Thomas Flow's algorithm. You can think of these as registers also. Right? That's really the tags. For example, here you have R5. This is the add over here, and R5. This add node is receiving R5, a version of R5 that's renamed to A. And it's receiving a version of R11 that's renamed to Y. Basically, this is producing R11, and A, this is producing R5. And this is also writing to R5. It's generating a new version of R5 that's renamed to D. Right? Okay. So I'm not going to build this data flow graph, but I'll leave this as an exercise to you. But I've shown you how to build it, right? You know this instruction. This is basically a multiply. But let's do one more, actually. Which one do you guys want to do? Let's do this multiply. So you know this instruction, so multiply. None of its sources are ready. And the sources are coming from B and C, tags B and C. Which means that this instruction over here is going to produce the left operand, and this instruction over here is going to produce the right operand. So this add is going to produce this operand, and this other add is going to produce this operand. And both of those adds are ready. And we know what those adds are actually. This is an add that's adding register 2 to register 6, and register 8 to register 9. This is the other add that's adding register 8 to register 9. Make sense? And B and C, where is B and C coming from? You can infer that by looking at the register file, right? One is coming, B, R7 is renamed to B, and it's not ready. Well, this must be waiting for R7. And R10 is renamed to C, and it's not ready. So the sources are R7 and R10. And what's the result it's producing? Y. Well, the tag Y exists for R11, so this must be a multiply that multiplies R7, R10, places the result into R11, right? And that's it, basically. Okay? So you can connect all of this just by observing the machine. The tricky part is what happens when things are renamed multiple times, right? So that's where beautiful reverse engineering questions come from. And beautiful bugs can come from also when you design the machine. Okay? So this is fun. So this is basically called restricted data flow, because this is a data flow graph that exists in the machine at this point in time. And that's why it's called restricted data flow. It doesn't form the entire data flow graph or the entire program. In other words, data flow-based execution is really restricted to the microarchitecture level. There are two cases where it's restricted, actually. One is data flow execution is restricted to the microarchitecture level, and the graph itself is restricted. And ISA is still based on the one-to-one model. Remember the data flow model, which we'll cover later on today. In that case, an instruction is fetched and executed in data flow order, right? Here we're executing instructions or dispatching them in data flow order, but we're really fetching them anyway, you know all of this. We're really fetching them in program order, right? That's the major difference. Okay? Okay, some questions to ponder before we move on to load store handling. Why is auto order execution beneficial?
Less stalling.
It's what?
Less stalling.
Less stalling, yes.
Yeah, more efficient use of the functional units.
That's right, exactly. Well, yes, you have.
It allows the hardware to make better decisions about what order to do things in when the programmer wouldn't necessarily know how long things are going to take.
That's right, exactly. It enables dynamic scheduling, basically. So I'll ask you the question, what if all operations take single cycle? Would it be beneficial? No, right? Because there's no latency tolerance. You actually finish the operation and there's no reason to do things in out of order, right? Oh, out of order. So basically, out of order execution really enables latency tolerance. That's a fundamental concept, I think. It tolerates the latency of a multi-cycle operation by executing independent operations while that multi-cycle operation is going on. You cannot execute the dependent operations on that multi-cycle operation, but you can execute independent operations. Okay? Well, the next question is, what if an instruction takes many, many cycles, 500 cycles? How large of an instruction window do you need to continue decoding? And this is where you really need a large instruction window. So let's do this calculation. It's actually very simple. It takes 500 cycles for an instruction to finish. And let's say you're fetching 4 instructions per cycle. You're decoding 4 instructions per cycle. You really need 2,000 entry instruction window, right? If you don't want to stall at all, if you want to keep decoding, yes.
Doesn't it depend though on what the minimum cycle time for your, for an instruction is? Because if 500 happens to be the minimum, it doesn't really matter.
What do you mean minimum?
So let's say if the minimum cycle count for an instruction is 250 instructions,
okay.
and you can only fill that with 2 instructions, right?
I didn't get it. So this is the number of cycles it takes to execute, let's say, a load.
Yeah. But you're presuming here that something else would take maybe 1 cycle or something like that, right?
No. I'm just saying, what do you need to ensure that you keep decoding? All of those may take 500 cycles.
Oh, I see what you're saying. Okay.
Does that make sense? Yeah. And if all of those take 500 cycles, that's fine, because you're and as long as they're independent, you're overlapping their latencies, right?
Mm-hmm.
You're basically kind of pipelining their latencies. But yes, some of them may be dependent to you. So if an instruction takes 500 cycles and all of the other instructions are dependent on it, you'll keep decoding. You'll keep buffering instructions, but you may not be able to execute anything, right? If everything is dependent. So out-of-order execution works if you have independent operations. And people have shown that there's a lot of parallelism in programs. There are a lot of independent operations. Okay. So how many cycles of latency can out-of-order execution tolerate? This really depends on the size of your instruction window and reservation stations. And that actually limits the latency tolerance scalability of Tomasulo's algorithm. So if you want to tolerate longer and longer latencies, you'd like to make this machine bigger and bigger. Both scheduling window, reservation stations, and the reorder buffer, because these are related. Right? Does that make sense? Yeah. I think in one of the past exams we asked the question, which one is bigger, the scheduling window or the reorder buffer? Or which one should be bigger? Anyone want to take a guess? This is the reservation station. This is the reorder buffer. No? Which one?
I'm thinking they'd be the same.
They can be the same, but they don't have to be. So think about when do you put an operation, put an instruction into the scheduling window, reservation station, when an instruction is decoded. Right? Same for reorder buffer. So all instructions decoded go to both the reservation station and the reorder buffer. But when can you take out an instruction from either one?
When the instruction finishes executing in the functional unit, then you take it out of the scheduling window.
Exactly. But you cannot take it out from the reorder buffer until it becomes the oldest in the machine. So this is either larger or the same size as the scheduling window. Has to be. Does that make sense? Okay. Okay, let's talk about memory. This is all about registers. Well, I've actually shown you this slide before. And I've given you these fundamental differences. Register dependencies are known statically, right? Memory dependencies are determined dynamically if you have dynamic memory allocation, which most useful languages have. register state is small, memory state is large. Otherwise, it doesn't make sense, right? Otherwise, you cannot exploit a small, fast register file. And register state is not visible to other threads. We've discussed this, right? This is why using a history buffer is very dangerous for memory, because you may have already propagated the value that you've written speculatively to another processor that reads that location. Okay, basically, let's talk about memory dependence handling. We've talked about register dependence handling, right? You can, because of these differences, memory dependence handling is actually fundamentally more difficult than register dependence handling. You still need to obey memory dependence in an out-of-order machine. You have loads and stores, and they need to appear in order, right? In program order. You need to commit them in program order. But we would like to do so while providing high performance, which means that we would like to schedule loads and stores out of order if they're independent of each other. Right? The key question is, how do you determine the independence of a load from a store? So if you have something like this, you have a store to X, well, you don't know the address, let's say, and you're doing a load. Let's do this. Store register 5 base and offset is 0, and store it to, well, this is the address, let's say, and you store some data to it. Data doesn't matter, and you're doing a load, and the address is, let's say, register 60, and loading it into some register. The key question is this load independent of the store? Right? And you may not know this because because instructions execute in data flow order, the sources of the load, R6 may be ready before R5 is ready. Right? As a result, you may not be able to know whether this load is dependent on the store. And the main reason is memory address is not known until a load or store executes, right? Because it's really dependent on this value, register value. Let me just make sure of one thing. Okay, good. I haven't paused it yet. Okay, so there are several corollaries to this. Because you don't know the memory address until the load or store, or any load or store executes, you cannot use the same thing that we used for registers, right? How do you rename? We can do renaming before. We can link the store, we can link an add to a multiply, because when we decode an instruction, when we decode this add, we know what register it's going to read. But we cannot do the same thing here. When we decode the load, we have no idea what this is. Right? I mean, there may be some loads where you actually have the address that's encoded in the instruction, but those are not interesting. This is the harder part. Okay? That's the main difference. Renaming memory address is difficult. Well, in this, you can imagine ways of overcoming this, but we're not going to go into that. The second corollary, which I already told about, is determining dependence or independence of loads and stores need to be handled after their execution. Right? So after you compute the address of the store, you can figure out whether this load is dependent. Actually, you need to compute both addresses. The third one is, when a load and store has its address ready, there may be younger or older loads and stores with undetermined addresses in the machine, because the instruction is executed in data flow order. Right? Then the key question is, what do you do? For example, let's say this load executes before the store, and you determine its address, but you have no idea whether the store is writing to that address. What do? Well, we'll talk about those options. It's an exciting topic because this actually affects performance a lot. When do you schedule a load instruction in an out-of-order engine? That's the key question. If you do not know the address of the store, but know the address of this load, you actually send it to the function unit. Yes?
Well, it's unlikely, given the memory space, that they'll be writing to the same place. So you could just do it.
Okay.
And if it's wrong, undo it.
Undo it. I like that, actually. That's I like your insight. It's unlikely that they're going to conflict with each other. And people exploited that. But actually, existing machines do prediction. But we'll get to that. They basically try to predict whether this load depends on the store. So that's one solution. Okay, basically a younger load can have its address ready before an older store's address is known. This is known as the memory disambiguation problem. You need to somehow disambiguate the addresses. Or, I guess more less of a mouthful, unknown address problem. You don't know the address, so what do you do? And there are several approaches for this. Let's talk about some of them. You found out the aggressive approach. The conservative approach, well, this is very conservative, right? Basically, you store the load until all previous stores have computed their addresses. Or even retired from the machine. That's even more conservative. Basically, once all of the loads, all of the stores before this load have computed their addresses, now you can check whether this address matches any of the stores, right? And how do we do that? We do that through the, remember the write buffer or store buffer that I discussed. That's a complicated address matching logic. Okay? This is conservative because the load may wait unnecessarily. Your approach, which is the aggressive approach, you can assume the load is independent of unknown address stores and schedule the load right away. Of course, you need to have a mechanism to fix this if you're wrong. I call it intelligent, but that may not be the best because it's more complex too. But the more sophisticated, maybe sophisticated is better. The more sophisticated approach is you can predict with a more sophisticated predictor. So this is actually a prediction mechanism, right? You're predicting exactly what you said. You're saying that it's unlikely that this load is going to load from the store that I do not know the address of. So I'm going to assume and predict that it's not going to. But you can do a more sophisticated, finer prediction by keeping information about loads and stores and predict if the load is dependent on any unknown address store. And maybe you can even predict which unknown address store it will be dependent on. This was employed in Alpha, for example. Alpha 21364, which didn't see the day of light. But you can actually link the stores and loads using this prediction mechanism. Okay? Any questions? This is all clear, right? The three approaches. No? Yes? To some of you? Most of you? Okay. That means I can go faster? Okay. If you don't understand it, shout it and we'll talk about it more. Basically, a load's dependent status is not known until all previous stored addresses are available. And there are two key questions with this. First of all, how does the out-of-order engine detect dependence of a load instruction on a previous store? And I'm going to assume this. I'm going to assume this one actually. You can wait until all previous stores are committed. Then this way you don't need to check. But this is a terrible solution because you destroy the parallelism that you're trying to exploit with out-of-order execution. And we'll see some results. Not with this one actually. This is a really bad approach. You don't want to wait until all previous stores in the machine are done. People have found out that about 40% to 50% in x86 at least of instructions are memory instructions. So 50% of your instructions you're serializing. That's a terrible approach. The second option, which we talked about earlier, keep a list of pending stores in a store buffer. These are all of the stores that have been decoded but not yet committed. And check whether load address matches the previous store address. This is how you can determine whether load is dependent on the store. Basically, I guess I'll get rid of the beautiful out-of-order execution example and show the store buffer over here. Basically, it's a program order list of stores in the machine. It's called a store queue or store buffer that has the oldest store in the machine and the youngest store in the machine and everything in between. And it obviously contains some control bits like the val bit and the address of the store and the data of the store. And they can both be valid or ready or not ready, right? Address can be ready and data can be ready. Because store actually has two operations, right? The data needs to be ready and the address needs to be ready for the store to execute. The second is how to, so we're going to assume this. And most machines have this. For example, in Pentium Pro, it's called the memory order buffer. It actually has a list of all the stores and loads in program order. And it ensures that everything happens in order by checking, by doing this check. So the second question, which we've just talked about, is how does the out-of-order engine treat the scheduling of a load instruction with respect to previous stores? And these are the three options. So let's look at the trade-off of these options. This is the conservative approach. Assume load is dependent on all previous stores. In this case, the load can execute only when all of the previous stores have computed their addresses. The second option, assume load is independent of all of them And the third option is the more sophisticated approach. Let's take a look at the pros and cons. Well, the first one, there's no need for recovery, right? Basically, you wait for all of the previous stores to compute their addresses, and then do the check using the store buffer. Basically, whenever all of the previous stores compute their addresses, the load that was waiting for all of the previous stores to become ready now can do the search. So there are two things. First, wait for all previous stores to have ready addresses. So there needs to be some complexity to do this, right? And the second is, well, you can imagine how to implement this. You have an instruction ID, let's say, for the load that's waiting. And you have an instruction ID for all of the previous stores. And you need to search this to figure out which stores are previous to this load. So it's a range search. Well, it's searching based on this instruction ID. And which, if all of them are ready or not. Yes?
You always talk about these searches that you do. Are they typically combinational searches or are they sequential searches?
Oh, they're typically combinational.
Okay, yeah, because otherwise
sequential
it'd
it
be-
takes a
yeah.
long time, right?
Okay.
Yeah, it's a combinational search. That's why the circuit becomes more complex.
Yeah.
So that's the first thing you need to support in hardware. The second thing is, once this is done, you need to check if the load address overlaps with any previous store. Okay? Now this is also complex. Actually, this is more complex because what you need to do is, this is the address. You need to supply the address of the load, and you need to compare this address to the addresses of the stores that are previous to this load. You don't want to compare it to the stores that are later than this load. So basically, it's an age-based search. Age meaning instruction order-based search, which makes it complex. And the second thing that makes it complex is it's really a range search, right? When you do a load, you have an address. Let's say the address is A. But you not only have an address, but you also have a size. Right? It could be a load byte, load word, load double word. So a load is really loading from address A to address A plus size, right? Well, does that make sense? You need to compare this range to, for each of the stores that are older than this load, store address and store address plus store size. If anything matches, then you say, oh, this load is dependent on this store. So the second thing that makes it difficult is this is a range search, or address range search. And the third thing, even if this is complex enough, the third thing is, well, multiple stores can produce the value for the same load, right? Which means that you can have multiple matches. I don't know if you can see this from there. I guess this is great for the camera. You can have multiple matches, and you need to handle that case. So that's why this part of the machine is one of the most complex parts in an auto order engine. You don't need to deal with any of this in registers, right? But you have to deal with this, deal with all of this in the store, in the stores and loads. Okay, hopefully this gives you an idea. We're not going to make you build this logic. Maybe in a later class. Okay, let's look at this conceptually now. Now that you hopefully appreciate the complexity of this. If you assume the load is dependent on all previous stores, there's no need for recovery. This is great. The problem is it's too conservative. This delays an independent load unnecessarily. And as you've observed, most loads are actually independent of previous stores. That's a good assumption. And you can imagine why, right? You're doing a lot of loads, and usually you load something to a register, right? Or when you just store, you're storing it to somewhere, and it's likely that you're not going to use it. Because if you were going to use it, if the compiler was reasonable, it would have allocated it to a register, right? So if you're doing a store and doing a load, and if they're close by each other, hopefully, they're not communicating with each other. You have to compile allocated time. Because if they were communicating, the value should have been allocated to a register. Now, that's not always the case, because what if you're running out of registers? In that case, store load communication becomes a problem. And in fact, when x86 had 8 registers, this was an even more critical part of the machine, because you do need to do aggressive store load forwarding. Yes?
Then you can't do atomic operations, right? Because like, if you have multiple threads that want to read and update memory, then you need it.
You need it to be in memory, right? Yeah, exactly. So that's another reason. That's another reason why you may have stores and loads that are close to each other, because the data cannot be allocated into a register. It has to be in memory. That's good. So there are other reasons also. That's why these dependencies exist. Okay? So this is not a good solution, because it delays independent loads unnecessarily. The second solution, assume load is independent of all previous stores. This is simple, actually, because you don't need a predictor, right? And can become a case. In most cases, people have found empirically that a load is not dependent on an unknown address store. And this is good because there's no delay for independent loads. The downside is it requires recovery and re-execution of the load and its dependence on this prediction. Right? Okay. The third option is more intelligent. Predict the dependence of a load on an outstanding store. It turns out you can more accurately do this prediction, because what happens is load and store dependencies persist over time. Even though you may not be able to determine them statically, dynamically you can, with a good idea, you can say, oh, this load is going to depend on the store, because it has done so in the past. Does that make sense? Why? It could be because of what you suggest, for example. You could have a variable that's stored in memory, and some other processor may need it. Let's assume let's ignore that other processor. But it has to be in memory, and you're writing a value to it, and you're loading it to it. You're loading from it later. Even if you're using different base registers to compute the same address, this persists over time. For example, or another example, if you're running out of registers, the compiler may write a register to memory, and you do something else, and then the compiler may load that register again. Basically, this is a save and restore, right? The compiler can restore that register. If your instruction window is large enough, that save and restore may appear at the same time in the window. Right? Does that make sense? Okay. So this is more accurate. The downside is it still requires recovery and re-execution on this prediction. Right? Because if you're wrong, you need to determine that. How do you determine that you're wrong? Well, once the address of all unknown address stores are determined, the load now needs to do the check. And if the load finds out that there's a match, and if the load was scheduled, if the predictor said, oh, the load doesn't actually overlap with any store, but it was scheduled because of that, and later when the load executes, when all of the unknown address stores have their addresses computed, load checks whether any of the addresses overlap. And if the load finds out that there is an overlap, then you need to flush the pipeline. Okay? You need the substrate to detect the dependency, but you can if the dependency doesn't exist, this buys you performance. Okay, so this is actually implemented in existing processors. Alpha 21264, the paper you're reading, has a nice and simple predictor. What it does is, the first time the load is executed from the instruction cache, it assumes that the load is independent of any unknown address store, and checks for dependencies. If everything is fine, that's good. This assumption holds the next time the load executes. Okay? It does the prediction again. But if the load, when it does a check, if the machine finds out that it did the wrong thing, meaning that there was a store that actually wrote to that address, and the load shouldn't have been scheduled early, what alpha did was, it set a bit in the instruction cache with the load, saying that, wait, when you schedule this load, ensure that all of the previous stores in the machine have computed their addresses. Just one bit, saying that do not schedule aggressively, schedule this conservatively. So you can think of this as a prediction mechanism that switches between, on a per load basis, between the conservative approach and aggressive approach. And this actually brought a lot of performance compared to both conservative and aggressive approach. It's a very simple mechanism, right? Very implementable. These two papers give you other mechanisms, and I'll let you read them if you're interested. This actually, these try to link the loads and stores to each other, and these are implemented in existing processors. For example, Intel actually went into a lawsuit with the University of Wisconsin because of this paper. Because the University of Wisconsin actually patented this paper and sued Intel later on, and they won some big money, I think, because of this. But basically, the idea is you can link a particular load to a store. When you execute the load first, you can figure out the load is dependent on this store and make a note of that somehow. And they have, these two papers have different mechanisms. I'm not going to go into detail. And later on, when you see this load again, if the same store has an unknown address, you make that load wait until that store computes its address. Okay? Make sense? Okay, good. So let me give you an example from this paper about the impact of this. Why am I covering this in a little bit detail? This is a bunch of applications that were in the spec suite at the time the paper was published. And this paper is actually from Digital Equipment Corporation. They evaluated some of the predictors they were designing for the Alpha 21364. You're reading the Alpha 21264 paper, which was actually a good processor, and which was commercialized. This is Alpha 21264, which is a successor to that processor, which never got saw the day of light, because Digital Equipment Corporation went belly up, I guess, and was bought by Compaq, which was later bought by Intel. Yes, well, that's the chain of events, right? Okay, anyway, basically, this shows the IPC instructions per cycle on an 8-wide machine, I think, for these different applications. And this is well, we don't see the average here, unfortunately, but that's okay. No speculation means the conservative approach. Naive speculation is the aggressive approach, your approach. And if you look at this, for most cases, naive speculation is actually better than no speculation. So the aggressive approach is better than conservative approach because most loads are independent of the stores. And perfect is the third one. Basically, perfectly you know which load is dependent on which store, and you perfectly say, wait, if that store has the unknown address. So you can simulate this. This is the beauty of simulation. When you have a simulator of a machine, you can determine by just doing functional simulation whether a load is actually dependent on a store. And in timing, you can simulate what you would like to do. In the simulator, you can, for example, if you're designing a pipeline machine, if you're trying to predict its performance, you can have a mode of the simulator where you perfectly predict branches, right? It's easy to do in software, right? Because in software, you can actually execute the branch and see which direction it goes, and steer the simulator, steer your pipeline that you're designing to go on the correct path all the time. And you can look at the performance of that simulated machine. So if you look at the performance of the perfect prediction mechanism, it's still significantly higher than both. So for example, here there's a huge gap. The IPC goes from 3.5, let's say, to 5.7, right? So perfect, here it's even higher. The IPC doubles, for example. This is a Perl. Well, how many of you program in Perl? Are you, okay, that's good. How many of you program in Python? More, I guess this is the Python days. How about Ruby on Rails? Some, okay. Python is the most popular. Well, this is Perl. At the time it was more popular. I don't know if Python existed at that time. Anybody know? No, you don't think so? Okay. Well, Perl's performance doubles by doing perfect prediction. And this paper actually talks about, describes a mechanism where you get very close to the perfect. That was the Alpha 21364 predictor. And this paper also talks about a mechanism where you get very close to the perfect. Okay. basically the takeaway, predicting store load dependencies is important for performance. And simple predictors based on past history can achieve most of the potential performance. It's not shown in this figure, but it's shown in this paper. Okay. Some more food for thought for you on out-of-order execution. I guess before we move on, any questions on load store handling? Okay, now you can actually answer any question, right, related to this. Oh. There are many other design choices in out-of-order execution, which I'm not going to go into right now. But one example is, should reservation stations be centralized or distributed across functional units? What are the trade-offs? I'd like you to think about that. I'll give you briefly the trade-offs here. This is basically, you have some buffer space. Do you divide it across functional units, or do you actually have a centralized buffer space that serves all of the functional units? Okay. This could be a good homework question, by the way. Rachel, maybe we should put it in the next homework. Okay. Another question, should reservation stations and reorder buffers store data values, or should there be a centralized physical register file where all data values are stored? Well, let me answer what some processors do today. A lot of the processors actually use distributed reservation stations for functional units. Because now what you can do is, the advantage of a distributed reservation station is you can specialize the reservation station for the functional units. If you have a centralized reservation station, you need to have all of the fields that is needed for all of the functional units per reservation station entry. That's the downside of a centralized reservation. The downside of a distributed reservation station is now load balancing, right? How do you actually size those reservation stations? If you have a shared or centralized reservation station, then you can have any kind of instruction mix and you will not stall, right? Unless you run out of reservation stations. You can basically share the reservation stations across functional units. If they're distributed, then maybe you have fewer reservation stations for ads, but maybe your program has lots of ads at that point in time. Now you'll need to stall, right? Or you size your reservation station much larger than needed. Okay? We'll kind of get back to this when we talk about shared versus distributed caches or private caches. But basically, do you share the space dynamically across functional units, or do you allocate the buffer statically across functional units? The second one, should the reservation stations and reorder buffers store data values, or should there be a centralized physical register file where all data values are stored? I don't know if you've thought about this before, but if you think about the reservation stations that we discussed, if you do this, do this as hard. But there are reservation stations there. And they store data values, right? They store all of the registers that you read, or all of the values that come. You don't really need to do that. That's very inefficient in terms of the use of space. Because let's say you're reading register 2 20 times. You have 20 instructions that are reading register 2. Now they're all in the reservation station 20 times. Not that great. You might want to have a physical register file that you read later. So you can use the reservation stations as a place to wake up instructions and select instructions, and data store can be separate for the registers. Okay? And most machines today actually have physical register files. They don't store data in the reservation stations or the reorder buffer. Okay? Well, we've discussed this. Exactly when does an instruction broadcast its tag? Right? It's actually too late if you're obeying the nice microarchitecture design principles that we discussed, critical path design. If you broadcast your value of the tag at the same time, it's a bit late. Because what needs to happen to your tag, right? Your tag needs to be broadcast everywhere in the machine, and all of those comparators need to settle. And you need to all of those instructions that receive the tag need to determine their readiness, and they need to get scheduled. Ideally, what you want to do is, when instruction broadcasts is tagged, the dependent instruction to be scheduled in the next cycle. Which means that all of this needs to happen in one cycle. If you broadcast your tag while you're broadcasting your value, it's hard to do this in one cycle, or your cycle becomes too long. But there's no reason to broadcast your tag at the same time you're broadcasting your value. You can broadcast your tag earlier and you can wake up the dependent instructions earlier, right? Such that by the time your value becomes available, the instructions are woken up and they can execute. Does that make sense? Well, this is good design. And I'll give you some papers that talk about this in a couple of slides. There are a bunch of other design decisions that I'm not going to go into. These are just examples in out-of-order machine. Some more food for thought for you. Now, combining concepts is interesting, right? How do you implement branch prediction in an out-of-order execution machine? Well, now you have many branches, right? And many branches are actually resolving out of order, too. How do you update the branch history register and pattern history table? Do you update them speculatively, or do you update them in retirement order? Any guesses? How do you update the branch history register if you have 1,000 or 126 entry window machine? Because you're fetching branches, do you update the branch history register speculatively? Well, the answer is you should really update them speculatively. You don't want to wait for branches to be resolved to update the branch history register, because you're doing the prediction on fetch. And you really would like to know what were the previous branches that you've seen, because the previous few branches are usually correlated with the branch that you're predicting right now. If you don't update the branch history register, you don't have the history for those branches when you're doing the prediction. Whereas if you update it, then you actually can do a better prediction. But of course, if you have a misprediction, you need to recover the branch history register to the point where you had the misprediction. Does that make sense? So you don't. These decisions actually affect performance significantly. If you mess up your branch history register, you're really messing up your history, right? And your history is really what makes this thing work. If you don't, for example, if you have a branch misprediction, what you really need to do is not only flush the pipeline, but also recover the branch history register to the point to the value it was when you actually fetched that branch. If you don't recover it, then your history is gone. Similarly to the return address stack. Right? If you have a branch misprediction, doesn't matter whether it's a return or call or any kind of branch, you need to recover the return address stack accordingly. Otherwise, your return prediction will be messed up. So all of these speculative structures you need to recover correctly if you want to get high performance. If you don't care about performance, then you don't need to recover anything, because these don't affect correctness, right? These are only for performance enhancement. But you need to keep the history correct. Otherwise, these things don't work for performance. Okay. How do you do the recovery from mispredictions? How do you do that fast? We've discussed that actually, right? We've discussed how to do fast recovery. And most machines today use checkpointing. Right? They do use reorder buffer, but they also do use checkpointing. Remember checkpointing? Okay, good. And they checkpoint. What they checkpoint is they create a checkpoint of the register alias table when they fetch a branch, when they decode a branch. Okay, more fun. How can you combine superscalar execution with out-of-order execution? Well, this becomes even more interesting, right? Well, the first thing is these are different concepts. Basically, a lot of people, when they say superscalar processors, they implicitly mean superscalar means white fetch, right? Multiple instruction fetch, done in hardware. You fetch, decode, execute, issue, dispatch, execute, commit multiple instructions. Out-of-order execution means, well, out-of-order dispatch. You can have a superscalar machine with in-order execution, and you can have an out-of-order machine that's single white, that's scalar. Which means that these are totally orthogonal concepts. In fact, Intel Pentium was superscalar. It had a 2-white pipeline. Alpha 21 164 was superscalar in order. And later 21264 was superscalar out of order. So these are different concepts. But superscalar execution and out of order execution interact. Once you have an out of order superscalar processor, you need to concurrently rename instructions. Basically, you're fetching, let's say, 8 instructions per cycle, and you need to rename all of them in one cycle, or maybe multiple cycles. You can pipeline the renaming project. But you need to get the names correct, because there are dependencies between instructions, right? An instruction that you're fetching, like the first instruction you fetch, can be producing a value for the fourth instruction you fetch in the same cycle. And you need to link them correctly, which means that renaming needs to be in parallel. Okay? And this becomes, as the width of the machine increases, the complexity of this logic also increases. And you need to concurrently broadcast the tags, but this is really not, we saw the concurrent broadcasting of the tags, right? Earlier. Well, I'll let you think about this. You can combine superscalar out of order and branch prediction, which is actually done by all of the machines that you have that are high performance today. Okay, I guess before we move on to the next part of the lecture, these are some of the readings that I would recommend. This is a required reading, so now you can read this actually. But there are other machines that were designed. This is actually a very nice reading. This is actually a very nice reading too, Power 4 System Microarchitecture, which is an out-of-order machine as well. It had a 100-entry instruction window and dual-core out-of-order machine, one of the first dual-core machines. That describes the microarchitecture of Power 4 really nicely, so I would recommend this. I would also recommend these two, although I don't think these are as clear as these two papers. This one talks about the microarchitecture of Pentium 4, and this one talks about the microarchitecture of the MIPS R10,000. So remember, MIPS was microarchitecture or microprocessor without interlocking pipeline stages. But now they have a superscalar out-of-order engine. So it has interlocking, all of the interlocking that's present in all of the other processors too, because that's what's needed to get high performance. Okay. I'd also, well, since you have a lot of time to read, or whenever you have spare time this summer, I'd recommend some of these things. If you really want to go into the guts of how dynamic scheduling is done in a modern processor, these two papers describe how it's done in a modern processor. And this is very similar to the way Pentium 4 did it. And this is actually a nice paper that describes complexity issues related to superscalar processing and out-of-order execution. Okay. I think let me stop here for now, and let's take a break. 5 minutes is good? Okay, let's be back at 1:40.
Yes. So, but
All right, let's get started.
Okay. If you don't change one of the bits of the CPSR, you need the CPSR. from
Okay, the
previous
next part of the
previous instruction is in the execute.
the next part of the lecture is about other approaches to concurrency, and this is what we'll cover in the next few lectures. How can we extract instruction level parallelism in better ways, or in different ways? I'll probably talk about data flow relatively quickly this time, but we'll not get to SIMD processing. These are some of the approaches that we're going to cover. Pipelining we've already covered, right? It's a basic form of instruction level parallelism. You do different parts of the instruction in different stages. Out-of-order execution we've also covered. And data flow at the ISA level, I'd like to spend a little bit more time today. And then in the next few lectures, we're going to talk about SIMD processing, VLIW, decoupled access execute, and systolic arrays. These are all interesting, fun concepts. Different ways people try to exploit parallelism. And actually, most of these are employed in some way today, even though data flow at the ISA level has not been as successful for the reasons that we discussed earlier. Let's take a look at data flow relatively quickly, and I'm going to skip towards some of these slides. Well, this is cycle 7 that we looked at before. Basically, out-of-order machine forms the data flow graph dynamically, even though you have a control flow program. In a data flow machine, which I had shown you before, this data flow graph is the program, basically. You don't have registers. It's not explained exactly. It's not expressed exactly this way, but it looks like this, basically. A program consists of data flow nodes, and a data flow node fires when all of its inputs are ready, when all of its inputs have tokens, right? And this is one representation of the node. This is basically your instruction, if you will. It's a multiply, it has an argument, and we'll see what those arguments are. It has a destination pointer, which instruction should receive the result, and it has a readiness of both of these inputs. And these were the nodes that we've seen earlier, right? Now you can actually figure out what a data flow graph does. Basically, using a set of nodes, a small set of data flow operators, you can define a general programming language with which you can program a machine, which is actually an ISA. An ISA is really a programming language, right? At a low level. So you can define, I'm not going to go through all of these, but there are a bunch of operations that you can use. And the data flow graph is actually your program now. The values in the data flow graphs are represented as tokens. So I've talked about the tokens. What are these tokens? What do they look like physically? Basically, a token specifies which instruction pointer address should receive this value, right? The port of the instruction pointer, which operand of the instruction should receive this value, and the data value itself. Now we're going to add something else to it called the tag, or the context, because what might happen is you may enter this data flow graph again and again. For example, if you're implementing a loop, you may enter it again. And those are all different loop iterations, right? A loop iteration, a token coming from one loop iteration should match the same token, should match the token coming from the same loop iteration. Does that make sense? Because you're executing the same data flow graph for different iterations, you want to ensure that the tokens that are coming, the tokens that enable the firing of this node come from the same iteration. That's why we're going to add a tag to this. And tag is the context identifier, which is the loop iteration count. How do you determine the loop iteration count? Well, you have another data flow graph piece that determines what is the loop iteration you're in. Okay? Basically, an operator or an instruction executes when all of its input tokens are present and copies the result token. It distributes the result token to the destination instructions. We'll take a look at what this looks like. Well, I guess in this case, for example, the instruction pointer is 3. These are the memory addresses of the instructions. Port is left, it's going to the left port, and the value is whatever value comes out of this. So no separate control flow, it's kind of obvious. Now we've seen this over here. This was our data flow program, right? This is one way of looking at data flow versus control flow, and I like the way this looks because in control flow machine, you really have separate program memory and data memory, right, in a sense. Program is distinct from data memory, even though they can be combined. A program looks like this. Basically, a program memory, this is an instruction, implicit sequential control flow between instructions, and this is what these instructions implement. And the instructions reference memory, or registers. You can think of registers as a cache for the data memory, right? So it looks like this. You have basically a bunch of references to registers that store the values. Whereas in data flow, you can think of everything in memory. Right? This is your instruction, and instructions actually reference the other instructions, if you will. This instruction is communicating this value that will be produced to this port of this instruction. It's also communicating this value it produces to this port of this instruction. Basically, it's 8 times 8, right? And this instruction is also communicating its value that it produces to this instruction. So everything is in memory. And there is no separate control flow. These can execute in any order. Okay, so what are the characteristics of pure data flow machine? Data-driven execution of instruction-level graphical code. You can think of this as graphical code, right? Nodes are operators, arcs are data, and we know that this is different from control-driven execution. The upside is only real dependencies constrain processing, right? Here, the program order constrains the processing, right? Because you need to fetch instructions in the program order. There may be lots of independent instructions down here, but somebody did not schedule them. You're bound by the control flow order when you're fetching. Here, only real dependencies constrain the processing. Well, this is because there is no sequential instruction stream, no program counter. And execution is triggered by the presence of and readiness of data. Basically, operations execute asynchronously. That's the biggest advantage of data flow. As a result, you can exploit irregular parallelism really well. Meaning, you can find what instructions can be executed in parallel, and you can execute them in parallel. Okay, so what does the data flow processor look like? This is actually very similar to auto order execution, except it needs to be even more complicated, I would say. Basically, this is what the pipeline kind of looks like. I'll show you an example later on. But basically, think about this as a processing element. When you execute an instruction, what it produces is a token. And a token is a packet, basically. It contains the destination instruction pointer, the data value of the token, And the port is also included in the destination here. And the tag. Tag is which iteration, which loop iteration, or which function invocation. You need to distinguish between them, right? Between the loop iterations, as we've discussed. And that token gets circulated, so the machine is really a big loop, basically. The token gets circulated into what's called the matching area. You can think of these as the reservation stations. The token goes to this matching area. It's a big memory. Basically, there's a pool of unmatched tokens. And this token, using the tag and the destination, searches for a matching tag and destination. Basically, it's looking for whether or not another destination, there exists another token that's going to the same destination, same instruction, with the same tag. If they match, if the instruction is actually waiting for two tokens, two source operands, now the instruction can become ready. If there's no matching token and if the destination actually needs two operands, then it stays in the pool of unmatched tokens. Let's assume that it matches. Then a group is formed. Basically, a group consists of another packet which contains the tag and the destination for the instruction that is to be fetched, and then the data values, source values, the two sources, assuming that you have two sources for this instruction. Make sense? That's how you match both of the operands. Only when both of the operands are ready, then the instruction can be fetched. Now you know that, now you can fetch the instruction. It's very different from control flow. You fetch the instruction first in control flow, right? Here you match the tokens first to determine what instruction to fetch. Now you can fetch the instruction that has matching tokens. And this is basically the instruction fetch area. This is the memory, instruction memory. Once you fetch the instruction, you can get the opcode and whatever is needed to execute the instruction. Now you can create an execution packet that contains the data values, source data values, opcode, the destination, and this is the new destination. Basically, the opcode is going to generate a token that goes to the destination of the instruction. Right? What instruction is going to receive this? And this can be multiple destinations. If it's multiple destinations, you actually generate multiple packets, multiple tokens. Okay? And then the same thing repeats. Basically, a nice pipeline flow. The difficult part is really this part. Basically, you can have a huge pool of unmatched tokens, right? Because you have the entire data flow graph of the program in the machine. In out-of-order execution, you limit that with reservation stations. One of the difficulties in pure data flow is how do you limit the size of this? Because instructions get fetched and executed based on the data flow order. So you really don't have control. Whereas in out-of-order execution, you have control. Well, control flow. As a result, you can limit the size of the data flow graph. Whereas here, it's difficult to limit the size of the data flow graph here. So in most machines that you will see, there's another separate pool that contains overflow tokens. So this is one of the difficulties in building a machine like this, the entire data flow graph in the machine at the same time. So this is one example. This is MIT tag token data flow architecture. It looks very similar. Basically, you have, it's good to start from here. When you execute an operation, you form tokens. Those tokens go to the token queue, and they get queued up over here, because these memories can take a long time. And they go to wait match units. This is the waiting token memory, which tries to match incoming token and the context ID. Context ID is really the tag here. People call it context and tag. I'd like to give you both definitions. And a waiting token with the same instruction address. If there's a match, both tokens are forwarded to the instruction fetch unit, such that you can fetch the instruction, and then you can execute the operation and then form the tokens, and then go back. If the tokens don't match, then the incoming token, assuming the destination instruction is a multiple operand instruction, incoming token goes into the waiting token memory and waits. And there's a bubble. Okay? Plus, I'm not sure if I'd like to go through this example. Maybe I'll do it briefly. Basically, this is called the tag token data flow architecture. It didn't see the day of light, but a lot of the concepts that was produced influenced the out-of-order machines later on. This is one example. You can go through this on your own, I think, but let me go through this very briefly. This is the encoding of a graph, basically. This is the encoding of the data flow graph over here. Of course, not complete. But basically, the first operation is this. Its destination is encoded as the instruction. It's at instruction address 109. The second operation is this. the destination is 120R. Basically, 120 is this instruction. That's the add. And the add destinations are 2. Basically, the destination is 141, which is op 3, and 159 left, which is op 4. And this talks about basically each invocation of a function or loop iteration gets its own unique context. That's the tag. And this is what a token looks like. Well, I guess this is what a token looks like, but it's kind of similar over here. This is you have the destination instruction address, left or right port, the context identifier, the tag, and the value. Let's take a look at what the execution of this 120 instruction at 120. Basically, let's assume that you have one of the tokens for this instruction, the left input, ready, and let's assume that this instruction is executing right now, op2, has executed and generated its token. So it generates a token that's destined to 120R because its destination is 120R. That's the token that's generated. This is the context, assume the context is matched, and this is the value. And this gets searched. Now you need to, the search in the waiting token memory looks for 120L, because this is R, looks for the same context, and there's a matching token over here. Now you form an execution packet saying, fetch instruction at address 120, its context is this, and these are the source values. Left value is 6.001, right value is 6.847. Did I forget to resume again? Well, I guess we'll do the same thing, Rachada.
I think it's still recording.
It's still recording? Yeah, I think it's still recording, but oh, okay. I did not forget to resume. Last time I forgot to resume, man. That was
You
bad.
may not have stopped.
Yeah, that's right. Well, I did stop, but it did
Oh, okay.
continue recording. It's an interesting piece of software. Okay. Anyway, so this is how you this is the instruction that is to be fetched. So in the instruction fetch stage, the program memory has accessed at the location that's specified by the instruction pointer. So you fetch this instruction and form an execution packet. So what is the execution packet? Obviously, opcode and the destinations of the instruction, the context, and the input data value that's coming from the weight match unit. And the instruction is executed. You add these two values. This is the result you get. Now you need to form the tokens. How do you form the tokens? Well, now you have the results. The value, the context, and the destination. The value, the context, and the destination. And then these get circulated again. It's beautiful, right? Yes. The difficulty is how do you build it over here. Okay, yes?
Where do the context IDs come from? How do you generate those?
Yeah, I did not discuss that, but basically the way it's generated is every time you enter the new loop iteration, for example, you can increment a counter. And that counter is your context.
But the software has to somehow specify what that is.
Yes, it needs to be, so everything, think of everything as a data flow graph. This context is generated by a piece of the data flow graph. Function calls, for example, a function call has its own context ID, and the data flow graph generates that context ID. It's interesting. Think about basically everything in the machine that executes the data flow graph. Your system software, operating system is a data flow graph. Your devices are part of your data flow graph. It's beautiful, actually. It's very compelling, but difficult to build, and much more difficult to debug and build. Okay, how do you do memory? Actually, you can do memory also. It's very simple. Basically, you can have an operation that says fetch at instruction address 200, in this case. And the destination is at 207. So how do you do memory? Basically, this instruction gets its address computed somehow. So you have a token coming in saying this token is for instruction at A, context C, and address 200. Well, the value is A, address is A, for the instruction at address 200. And in this case, you don't have any other operand, so you bypass the waiting token memory because it's a single operand, unary operator. Then you can fetch the instruction at 200, and this is an instruction that says fetch at address A. Execute op is a no op, basically. You form the tokens. At this point, basically, you form a fetch token that goes over here. It gets output into the network, if you will, or memory. And you wait for memory, basically. This is a packet that enables you to wait for memory. You fetch from address A and with context C, and the token and the destination is 207, which is the destination instruction. So you can think of this as load And you can think of this as the operation that needs the value from the load. Once the memory responds, it responds with something that looks like this. Now it responds with a token, right? And the token is, this is the value that needs to go into the instruction at 207, and this is the context, and this goes into the token queue and fetches that instruction. Make sense? So I can do load stores over here too. So that's another data flow machine which looks very similar. This was designed in 1980s at the University of Manchester. And I don't know if I'd like to go into this again. Basically, it looks the same. And this is the overflow unit that I mentioned. Because you have a huge data flow graph. Imagine you can have a huge program, a huge data flow graph, right? And you can overflow this matching store. And you would like this to be fast because this matching, remember, this is very similar to the matching that happens in reservation stations. If this is huge, your machine is very slow. So they keep this fast. They keep some recently stored tokens over here. But if they don't match, they go into this overflow unit. And this becomes one of the hardest part of the machine to design. Okay. So let me conclude with advantages and disadvantages of data flow. Advantages I've already told you. Very good at exploiting irregular parallelism. This is actually the best model that we know of to exploit irregular parallelism. Regular parallelism we'll see. Vector parallelism, we'll see that you can exploit in a much better ways, much more easy ways. And only real dependencies constrain processing. That's exactly, these two are related. That's why you can exploit irregular parallelism very well. But there are a bunch of disadvantages as well, which we briefly talked about earlier. One is this, no precise state. You know this very well by now, right? As a result, debugging is very difficult. This should be the first one, actually. Let me correct this. Debugging is very difficult because you have no idea what your state is. I guess if I do Control X, my PowerPoint will die. There you go. Okay, I'll keep going while the PowerPoint is thinking. Interrupt and exception handling is very difficult also. Okay, there you go. So debugging is very difficult, but obviously PowerPoint doesn't work too well, even with the single control flow paradigm. Someone programmed in data flow. Bookkeeping overhead, that tag matching is a huge overhead. That's why those machines have huge tag matching stores. Actually, those machines have this as well, to avoid the huge stores. Control parallelism. Sometimes you get too much parallelism, too many tokens, too many instructions that are waiting. So these machines control the parallelism such that they don't overflow those matching stores. And I'll let you think about it, but implementing dynamic data structures, implementing heap memory actually becomes difficult. Because think about it, everything is really a value here. How do you implement data structures that keep changing? Okay, if you're more interested in this, you should take 740 or 742. We discuss it in more detail. Okay, let me summarize, and then we'll conclude. Basically, in data flow, availability of data determines order of execution. And a data flow node fires when sources are ready, and programs are represented as data flow graphs of nodes. And data flow at the ISA level has not been successful, basically. People have tried to design machines over the course of 70s, 80s, and early 90s, even to the very early 2000s. Well, maybe not. But they weren't successful at the ISA level because the software, all of that debugging is very difficult to do. But data flow implementations under the hood at the microarchitecture level, by preserving sequential semantics, have been extremely successful. Because basically, an out-of-order execution machine that we discussed does essentially the same thing. It really has this matching store in reservation stations. In fact, when people introduced out-of-order execution with precise exceptions, they called the reservation stations as node tables. These are storing the data flow nodes of operations. This paper that talks about the restricted data flow microarchitecture basically refers to reservation stations as node tables. The term is not used. I don't know why reservation station has become more popular, because reservation station, what does that mean, right? What are you reserving over there? If you're reserving some space for instructions, maybe. But node table makes a lot of sense. It's really the data flow nodes that are stored in the tables. Okay, so this shows that the importance of programmers. Actually, when Arvind is one of the proponents of data flow. He's done a lot of research in data flow. When he gave a keynote at ISCA 2005, he said one of the biggest mistakes they did when designing data flow machines was they ignored the software. They didn't put enough effort into the software. If they had the software infrastructure developed, which is actually a very big challenge, I think, perhaps data flow at the ISA level could have been successful. Because you need all of this code base to be changed to data flow. And that becomes very difficult, especially with all of the debugging problems that you have in data flow. Okay, so if you're more interested in data flow more, I'd recommend this paper. It talks about the Manchester prototype data flow computer. So you can look at the data flow language as well as the machine design. In microarchitecture level data flow, we've been discussing that in all of those papers, but you can take a look at this paper also. That talks about data flow, restricted data flow, which is out-of-order execution with precise exceptions. Any questions? Yeah, it's fun, right? So data flow was the first execution model that we've covered. That's different from the von Neumann model. We're going to delve into more execution models, but I think I'm not going to do that today because we're definitely not going to finish vector processing in the next 8 minutes or 12 minutes we have. So I'll let you go early this time. Okay, unless you have questions. Yeah? Okay, we'll start with vector processing next time. We'll look at regular data parallels.